Hi, we are the A team, and our project is a low latency secure gateway for algorithmic trading on a custom network processor. To understand our project, let us start with a simple analogy. Let us redefine the age old story of the race between the hare and the tortoise. And let us set the story in LA. They decide to start racing from USC. The destination is Venice, and the prize is a trophy. The hare and the tortoise have a set route to follow and they begin racing. Halfway through the race, the destination is changed to Hollywood, and so the trophy is moved. They now have a new path to take. Tired of running, they decide to take help. The hare gets a cycle while the tortoise gets a Ferrari. It goes without saying that the tortoise with a Ferrari wins the race as it can go faster than the hare. How does this relate to our project? The hare and the tortoise are nothing but clients, and the destinations, Venice and Hollywood, are servers, and the means to reach the server from the client is nothing but the software and the hardware routers. For a more realistic scenario, let us consider the stock market scenario, where the destinations are replaced with companies A and B, and the clients are buyer 1 and 2. Initially, the company A has a better stock value, and so both buyers prefer buying shares from company A. At some point of time, after the initialization of the investment, if company B has a better market value than company A, as such situations are quite common in the stock market scenario, then both the buyers prefer to move their investments to company B. To assist the buyers in doing this in a faster and efficient manner, we plan on providing a custom network processor that is equipped with the implementation of a trading algorithm. The algorithm is able to detect the conditions of both the companies and the stock values, and once it decides that company B has a better stock value than company A, it informs the buyers about the advantage and the buyers can reroute their investment. The processor can be made further smart so that it reroutes the investment by itself and then makes it easier for the users by saving their time. How do we implement this in the custom network processor? We first integrate it into the NetFPGA. The packets that come in through the network go into the receiver queues, and these then go into the input arbiter. The input arbiter issues packets to the output port lookup in a round-robin fashion. The output port lookup attaches a module header to the packets which contains the destination port. These packets then move into the custom network processor. Our design of a custom network processor is a single-core, dual-threaded processor. The instruction memories are interleaved such that the instructions are switched at every clock. This is an implementation of fine-grained multithreading. The switching between the instructions is controlled by a thread schedule. We have a convertible FIFO data memory, which acts as a FIFO while capturing the incoming packets and while passing packets out of the processor back into the NetFPGA module. It acts as a data memory when the packets need to be processed through the processor and returned back to the data memory. The memory control unit ensures the switching between the FIFO and the data memory mode of the convertible FIFO data module. A crypto engine is placed near the output of the processor to ensure that the data which goes out of the processor is encrypted and kept secure while traveling through the network. The design has been improved to develop the proposed low latency secure gateway. We have included a scratch memory, which on boot up is pre-programmed with the MAC addresses of all the destination servers available in the network. These are the addresses that the packets will have to be rerouted to once the decision of the trading algorithm calls for rerouting. A hardware accelerator has been equipped. The low latency is achieved by using the hardware accelerator, which ensures that the rerouting procedure is done faster to implement a lower RTT. The incoming packets are first passed through a user authentication module. This is necessary to ensure that the user is a valid user and not a malicious impersonator. Once the user has been authenticated, the entire procedure begins, without which none of the implementations of the proposed module would take place. The packet header initially has a destination port of 0001. Instructions are then executed to transfer the contents of the scratch memory into the register file and also to mimic the implementation of the trading algorithm. Once the trading algorithm calls for a rerouting, appropriate instructions are carried on to follow up on the trading algorithm implementation. The hardware accelerator is then used to change the destination port of the packet, and the destination port now reads 0010. Once the packet has been rerouted, it is passed out of the processor by using a crypto engine. This ensures that the process is encrypted. The crypto engine encrypts and decrypts packets by using a symmetric key of 64 bits. The symmetric key is transferred to the NetFPGA through the RSA key exchange algorithm. The server and the client generate the public and the private keys using the RSA algorithm, and these keys are shared between the client and the NetFPGA to achieve RSA encryption.
Let us see the execution of the low latency gateway that we have implemented through the custom network processor. As you can see in the left hand side, this is the control node of the NetFPGA, and on the right hand side is the client that is connected to the NetFPGA. The first step is to load the bit file. The bit file basically consists of the network processor implementation, which provides low latency gateway. As soon as the bit file is loaded, the router daemon has to be activated. The client sends packets to the server in an encrypted fashion. So for this purpose, the RSA key exchange algorithm has been implemented. Assume the NetFPGA is the server and the node which is on the right hand side is the client. The client is now generating its public and private keys through a Python script. The Python script provides a socket connection between the server and the node so that the keys can be exchanged. Now the server is trying to generate its own public and private keys and sends its public key to the client part. The client receives the server's public key, and with this public key, the client encrypts its symmetric key and sends it back to the server. As you can see here, this is the symmetric key in an encrypted fashion. The server uses its own public key or private key to decrypt the message. Thus, we have obtained the client symmetric key. Now, let us see the actual implementation of the low latency gateway. Once the RSA key exchange has happened, our, our network processor monitors the server values. So for that, let us set N1 as the server, and N2 as the server. Let us try to send packets from N1, from N0 to N1. As you can see, the N1 has received acknowledgement from N0, getting all the packets from N1 itself. Let us see the actual implementation of the low latency gateway. As soon as the RSA key exchange has happened, the custom network processor monitors two values, namely S1 and S2. S1 is stock 1 and S2 is stock 2. Now for the first test case, let's say S1 has the higher parameter over S2. This condition makes the trading algorithm false and the packet rerouting won't happen. That is, when a packet is sent to N1, N1 receives it rather than N2 or N3. Let us fix that condition in the control node and set a TCP dump on N1 and N2 and send a network packet such that the passkey is also included in the data. Now as you can see, N1 has got the network packet and N2 didn't. This means that rerouting didn't happen. Now let's go for the second test case, that is S1 has a lesser value over S2. In this case, the trading algorithm should go high and the reroute condition should happen. That is, when a packet is sent to N1, it has to reroute to N2 according to our conditions. Let's change the server value through a Perl script. Now let us set the TCP dump. Now we'll send a network packet without a passkey. Still, N1 has got the network packet, which means that the user has not got authenticated. That is, the user is not authenticated to use the faster reroute protocol. Now let's see the third test case. That is, still with the reroute condition is on, let's give the user's passkey in the network data packet such that the user get authenticated and the rerouting happens. Let's rewrite the server values and I'll set a TCP dump on N1 and a TCP dump on N2. Send a network packet with the user's passkey. As you can see, now I sent the packet to N1, but since the reroute condition is true and the user's passkey is available with the network packet, N2 got the data. Now instead of using iperf to send network packets, we have used Python scripts for socket programming. Let's see the first test case, that is the non-reroute condition through socket programming. Let's open up a TCP dump on N2 and N1. Open up a server socket on N1 and a client socket on N0. As you can see, this is the data and this is the received message. On the TCP dump, we have received the same data. Now let's see the reroute condition by changing the data. Open up a server socket and a client socket. As you can see, the data has got rerouted to N2 instead of N1. The main advantage of the system is it has a very low latency because all the routing procedures are done through hardware. Let's see the round trip delay on pinging any of one nodes. As you can see, the packets return back in a very less time of zero point 0.1 or zero point 0.2 milliseconds, which is very less than when compared with the software routers that are available in the market.
We are using the Mininet virtual network to set up and configure a software router which is used as a reference platform against the hardware router designed using a custom network processor. The virtual network is already set up on our laptop and running. We're going to obtain the IP address of this, which is provided by the inet address. Now this inet address, when accessed through a terminal using the X11 SSH, is provides us to configure and design a topology. So when we log in into Mininet using the PuTTY terminal, I can go ahead and configure it to any topology of my requirement. For this project, we're going to set up a topology similar to what we have set it up in our hardware router. Now this topology here consists of 3 nodes and a controller and a switch. Now when I enter the command on the Mininet virtual machine, it's going to set up nodes. Nodes here are named as hosts and symbolized using H. So when I configure the nodes, the controller and the switch, the Mininet virtual network goes ahead and sets it up. Now the topology is set up. We need to provide the routing information for the controller. This routing information can be provided using the commands. So right now, after we set it up, we have a topology which is configured and ready for packet routing. So when I ping from one node to another using this command, we obtain a round trip time of around 11 milliseconds. So when we go ahead and do it again, the round trip time comes to around 1.3 milliseconds. We are using the Mininet virtual network to set up and configure a software router which is used as a reference platform against the hardware router designed using a custom network processor. The Mininet virtual network is already set up on our laptop and running. We're going to obtain the IP address of this, which is provided by the inet address. Now this inet address, when accessed through a terminal using the X11 SSH, provides us to configure and design a topology. So when we log in into Mininet using the PuTTY terminal, I can go ahead and configure it to any topology of my requirement. For this project, we're going to set up a topology similar to what we have set it up in our hardware router. Now this topology here consists of 3 nodes and a controller and a switch. Now when I enter the command on the Mininet virtual machine, it's going to set up nodes. Nodes here are named as hosts and symbolized using H. So when I configure the nodes, the controller and the switch, the Mininet virtual network goes ahead and sets it up. Now the topology is set up. We need to provide the routing information for the controller. This routing information can be provided using the commands. So right now, after we set it up, we have a topology which is configured and ready for packet routing. So when I ping from one node to another using this command, we obtain a round trip time of around 11 milliseconds. So when we go ahead and do it again, the round trip time comes to around 1.3 milliseconds. The average round trip time obtained from the hardware router configured on a custom network processor is around 0.6 to 0.8 milliseconds, whereas the RTT on the software router configured using the Mininet virtual network is 1.3 milliseconds. The Mininet virtual network software router has a higher RTT compared to the hardware router designed on the network processor. Our network processor, configured as a hardware router, provides a lesser latency for packet rerouting. This can be used as an effective router. Now looking at a comparison between the hardware and software router, can be seen that with the increase in the number of bytes per packet, the average RTT for a software router increases drastically, whereas for a hardware router, the average RTT remains significantly lesser. The hardware router hence acts as an effective tool for packet rerouting and can be used as a low latency design for rerouting of packets. We are using the Mininet virtual network to set up and configure a software router which is used as a reference platform against the hardware router designed using a custom network processor. The Mininet virtual network